Okay, good. I am just checking that it is recording, so let me see. Yeah, okay, it is recording. Perfect. Now I can share my screen. This one, very good. And let me keep the chat in front of me. So it's 1 second. Okay, now the chat. Good. Okay, I have the chat in front of me on the other screen, and then I can go with the website, mine. 1 second. Here it is. Good. So there is our page here. And then we go to 1 second because it's a bit slow. Good. Let's go to, there is this exercise, calibration of the iMode Rainfall Runoff model. I don't remember if we already had a look at the PDF, but given that it's very, very easy, let's have a look at it. So it's again, it's like the linear reservoir. There is, I think also the data set is the same, and you don't need to look at these links. They are also outdated, still working, but outdated. I will change this text. You don't have to have a look at these links because they are clickable on the website, so you don't need to cut and paste them in the browser. So it refers to a river cross-section draining a catchment whose area is 1214 square kilometers, and it's precisely the catchment is the Secchia River catchment. Secchia is the river that gives the boundary, draws the boundary between, in Emilia-Romagna region, between the local administration, local municipalities of Reggio Emilia and Modena. It's close to my home. And we have river flow data at an hourly time step for a period of 1 year. So it's 8,780 data. At the same time, precipitation and potential evapotranspiration have been estimated. And I think the data are the same that we used before. These are synthetic data. It's again synthetic in order to minimize the uncertainties. So we need to use the above data set to calibrate iMode. And here it is suggested to use the sum of squares as objective function. So wait a moment about this, because actually the objective functions are the subject of my next lecture. So we can start the exercise, but for calibration we need a little bit of more theoretical discussion. And also here there is a specification. The initial value of the river flow is set to 15 cubic meters per second. And then we will see how to fix this initial value. Okay. And then there is a subsequent request. The matter is rainfall runoff modeling. And rainfall, I'm not sure if I understood your question, Abdullah, but it's the matter. No, sorry, I was looking. I got some messages from the other courses, and I didn't understand that the questions were by other students, not you. So let's forget about my last 2 sentences. As I was saying, here there is another request. We should forget it for now. And because it speaks about model validation, again, this is the subject of my next lecture, so it's no problem. Also forget about this, explain in a brief report the above elaborations. I need to delete this sentence. This was referred to classrooms, not to virtual teaching, so don't be concerned about this. Okay, now let's close this PDF and let's go back to my website. And there are, as I said, rainfall and evapotranspiration data. I click on this link, the link here. Let me expand. Okay, I am clicking on it, and let me see. So you see that there is, I think it is the same file. There is a first column of heading, which we need to skip when we import the data in R. But what you should do, it's let's copy the file in a position, in a given position. So I save it, I click with the right, and then I save with name, save as. I think I already have it, and probably you as well, but let's save it. And also the river flow data. Let's see the file first. You see that there is a line of heading, and then there are the data. So let's go back and save it. So river flow data, perfect. Save it. Save file as. Okay, good. Now here there is a suggested R code for resolving the exercise and applying the iMod model. For some of the exercises, I give a suggested R code. The reason why I give it is that, you know, when the codes become a little bit more complicated, if we start from scratch, it requires a lot of time. It's more efficient if I make a proposal to you and we discuss the proposed code line by line. And a recommendation for you, a fundamental recommendation, when you get a code, a software that it's already working and you don't need to program it, I highly recommend that you understand how it works, what is the theory behind it, how how the program works. And the reason is that first of all you learn more and you may improve it. Like in this case, it's not a commercial software, it's an open source. When you use an open source software, you can improve it. And this is what I would like you to do. If you have any ideas for improving this code, which is not the only one that applies iMod that you can find on the web. If you look in the web, there are a lot of codes for applying iMod. Some of them are in MATLAB, some of them are in R. So, as I said, it's interesting to try to improve it. When you will work in your profession, understanding what a program does is essential for getting able to get an idea of the reliability of the results. Keep into account that usually programs, softwares, they make assumptions, they use numerical simulation, and then there is an approximation. So usually when you use a software, the result is never precise, never correct, strictly speaking. As I said, there are simplifying assumptions, whatever. In some cases, the program may be unstable. Numerical approximation may give rise to instability. And therefore, it is extremely important when you get a result from a software that you are able to assess whether the result is reliable or not. And in order to assess it, you need to elaborate a preliminary idea, an intuition of what the result should look like. You have to gain an expectation, like you make a computation of the thickness of a dam, and you gain an expectation, like it should be something around 10 meters rather than 100 meters, rather than you need to know the orders of magnitude, and you need to know the theory behind it in order, as I said, to get a preliminary idea. And you can get this preliminary idea only if you know how a program works, only if you know the theory behind it, only if you spend some time to try to understand the natural process, what is behind the software that you are applying. This is extremely important because it allows you to detect errors, and it's extremely important because if you make mistakes, as I already said to you, I think, you cannot say to a judge after a lawsuit has been made that it was the program that was wrong. In any case, it's your signature that is put under the design, it's your responsibility. And therefore, as I said, it's extremely important that you you understand how a program works, even if you use something that is widely tested. Okay, so let's open this R code. So I'm clicking here and let's open it. And if you open it, if I click on it, the PC asks me whether I want to open it with RStudio already. And if you get this option, this is perfect. And you should click on OK like I will do. If you don't get this option, what you have to do is to save the code as we saved the data. And then you open RStudio and you upload the file, the save file, as a script. This is what you should do. Now I am clicking on OK and then I'm getting RStudio. Here it is, and RStudio already has the script in the script window. Now let's assume that we all got to this stage, and if you have any problem, write on the chat. I can wait for you. Okay. Now, as I said, we should look at the script, and in order to look at it, I think it is much better if we expand the script window. Here we are. Okay, now give me 1 second, students, because I need to reply to the phone. Give me 1 minute. Thank you. Here I am, sorry. So this is the script window. Let's see. I hope you can see the font are large enough. Let me see if I can use a larger font size. I think it's in edit, and just let me see with session. Not a global option. Good. View. First of all, I set the working directory, which I forgot. Choose directory. So we should select the same directory where we saved the file. I am done here. So just don't forget it. Don't forget to set the working directory in the proper place. And just 1 second. Okay. Okay. Editor. Yeah, I found it. I found the font size under 1 second. Okay. Now let me expand it. Very good. Now just let me go on the left. Okay, good. So let's have a look at the suggested code. First of all, there is there is there are 5 lines which are dedicated to uploading the data, and then there is the script of a function to apply imode. And this is something that to be used in RStudio it's not very efficient. I think what we could do is indeed to upload the data, and by cutting and pasting from the script to the console, and then I suggest to delete these lines from the script. So let's go to the console now, and okay, and let's copy from the script this instruction for uploading the data one by one. Probably we could upload the data also by using RStudio, but for simplicity, given that we have the instruction already written there, I suggest that we make a cut and paste. So I select with the right, copy, and then I go to the console, and with the right I use paste. And I think it should work. Let's see. Yeah, I think so. What I don't remember is whether the rain file, I think it had only one line of heading. So let's do it again by putting skip 1. Yeah, this is correct. Look at the console what I did. And skip 1 means skip 1 line. In the previous version there was skip 3, so I need to take a note to change this in the script file. Let me take a note. Skip is 1. I hope everything is clear to you. If there is something that you don't get, please stop me. Now, the problem is that this is rain evapo. What I called rain evapo is a vector which contains both rainfall and evapotranspiration. So we need to separate it in 2 columns, and in order to do that, I go to the script, I copy the next instruction which creates a matrix from the vector, and then I go to the console, again paste, and then I transformed again the vector into a matrix. And now I am ready to extract each column of the matrix in order to create 2 vectors, one with rainfall and one with evapotranspiration. Okay, paste, and this is done. Now we have a vector called P, which contains rainfall, and if you check the length, you see that it's 8760, which is correct. And then we have a vector called EP, which contains the potential evapotranspiration. Okay, very good. Now let's scan the observed discharge. I think in this case as well, skip is 1, not 2. So let's go to the console. I paste it. Let me put skip 1. In fact, you see that it read 8760 items. Very good. So here we are, and now we don't need, let me go to the script file again. We don't need, let me see, I think, okay. We don't need these lines anymore. So I can go to the script file and cancel these. Perfect. And now we can save it. In this way, I don't understand why. It says that the source file is read-only, okay, to me. So I need to save it in another directory. Just 1 second. Okay. Okay, save. imod.r, I put a name for the file. Okay, good. Perfect. Now, let's look at this script line by line. First of all, this instruction here, you already know it. It's the instruction to create a function. As argument of the function, let's put a parameter vector called PAR. Now there is a curly bracket to open the function. Very good. And now there is an instruction to set the area of the catchment. Perfect. It's 1214 square kilometers. It's in square meters here. And now there is an instruction to set the time step, 3600, which is the number of seconds in an hour, because everything needs to be brought in cubic meters, in meters, so area in meters and time in seconds, because we want to get the discharge at the end of the story in cubic meters per second. And then there is the number of time step, which is for now set to the length of 1 year, the number of hours in 1 year, which is 8,760. And there is a note here, be careful to adjust it as needed, because if you want to perform a simulation of the model with a shorter duration, you need to change this n delta t. Of course, you may decide to introduce these instructions as arguments of the function. This would be another possibility. So you may have written something like area B and give 1214 square kilometers as a default. This is what I'm doing. And then T step equal 3600 and n delta t equal to 8760, and then let me also the following one, QE equal 15. What is QE? It's the initial value of the river flow. And then if you put them as argument of the function, you can remove these lines, which is fine. I mean, maybe a more elegant way of writing it, and it's up to you. It's your call. Now there is a conversion factor which is introduced and will be used later. It's introduced because rainfall is in millimeters per hour, and therefore you see that this conversion factor is to transform a rainfall depth given in millimeters per hour into a rainfall volume per unit time over the catchment area. So first of all, there is 1 over 1000, which is needed to transform millimeters in meters, because we want the rainfall flow to be given in cubic meters per second. And then there is a divider by the time step, because rainfall is given in millimeters per hour. We need to give it in meters per second. And therefore we divide by the time step. And then we multiply for the area of the catchment to get it in cubic meters per second. This is a conversion factor that will be used later. And then we have these parameters. For the sake of simplicity and clarity, I want to convert the parameter vector PAR in 5 variables which are named in a way that I can recognize which parameter they refer to. So Cmax, it's equal to the first element of the vector PAR, and then beta, alpha, K slow, and K quick. Good. Now we can start. We can start by applying the model. We have everything we need. The information, the preliminary information. We have the input data uploaded in R, so the function can use them. I don't need to put the input data into the function. But of course, you may decide differently. You can put the input file name. as an argument of the function, and then you may also include in the function the scan of the input data. Again, this is your call. I think in this way is a bit simpler, but if you want to change it, this is no problem. Now we need to initialize variables, and so what is W2 is the storage in the catchment at t+1, and you remember that we need the values of CT and the value of storage at the beginning and end of each time step. So we need to define 4 variables, which are CT, CT+1, WT, WT+1. So W2 is WT+1, and which is set to 0, and C1 is set to 0. Perfect. Now, here there is the setting of the initial content, the initial storage of the reservoir, which we use to route the low flow. If you remember the scheme of iMod, let me, just 1 second. Let me get it, okay? I want to explain to you what is this clearly. This scheme. So we are setting the initial storage of the only one reservoir that you see on the right of the scheme below, KS. We set this initial storage. The other reservoirs are assumed to be empty at the beginning. Only this one, the lower one, we set an initial storage. Why do we do that? Because we are required to start from a river flow. The river flow Q0 at time 0 should be equal to 15. And the way to get a river flow, one way to get a river flow at time 0 is to set the content of this reservoir KS. If we set an initial content, then we get an initial flow. Of course, there could be other solutions, like setting the content of the 3 reservoirs that are placed above, but actually we don't need it, okay? We don't need, I mean, it's simpler if we set the content of the lower reservoir. Okay, so let's do it here. You see that there is the content of the lower reservoir is called W slow, and it is set in a way that when we compute at time 0 its outflow, we get Qi. And in order to do that, we just have to set W slow to the ratio of Qi at the numerator, and at the denominator we put K slow times fatconv. And in this way, at the initial time step, when we go to compute the flow, the outflow from the reservoir, what we do is just to multiply W slow divided by K slow, and we get exactly Qi, and you will see that it works. There is one thing, yes, sorry, I repeat, so just 1 second. W slow and K slow are okay. W slow is the content, initial content of the reservoir that you see in the bottom of the figure here. And K slow is its linear parameter. You remember that in order to compute the outflow from a linear reservoir, we divide the storage, its storage by a time parameter, ks, in this case. And therefore, ks is this parameter of this linear reservoir. And here we compute the initial value of its storage, W's law, by dividing qi times k's law times fatconv. There is one thing that I wanted to tell you here. If you look at how here it's W's law defined, you notice that k's law, which is used here, has not the dimension of a time. It's 1 over time. So the parameter of the linear reservoir, as it is defined here, it's the inverse of the parameter that we used in the other code, in the code of the linear reservoir itself. So k's law here has a unit of 1 over time. And this is something that we may change. We may change it because I don't think it is appropriate. Let's be consistent. So if we want to be consistent, k's law, express k's law in time, what we have to do is to put a multiplication here, and we keep the division of the conversion factor. And in this way we are consistent, and we have to make sure that we make the same change later on in the code, because otherwise it's not really. And also I want to change it in the code on the website, because I take a note. Give me 1 second. Change k to 1 over k. Okay. I hope everything is clear. Now we set W quick. What is W quick? W quick is the content of the 3 reservoirs that are above. And we don't need 3 contents, we just need 1. So we don't need to define 3 storages, we just need 1. And we will see later why it's efficient to get just 1 content. We don't need to get several of them. Okay, and now let's go to other definitions. Here there is a definition of ER1. ER1 is the contribution to runoff, which is given by saturation excess when the catchment is completely saturated. If you remember, I go back to the definition of IMOD. Here, you remember, see here the 2 relationship, ER1 and here 2. Okay. So these vectors, you see that these are vectors, need to be defined. So I go back to RStudio now, and let's define them, ER1 and ER2. Also, I need to define ER, which is the sum of ER1 and ER2. I need to define evaporation, actual evaporation, and these vectors are defined as sequences of zeros for now. And then I need to define QT, which is the vector of the output. These vectors, as I said, need to be defined. And then there is the computation loop. Okay, this is SK, so we are getting into the computation loop. SK is the initial value of the simulation. Let's put it at 1. Okay, I take a note, because it is flexible. It gives us flexibility if we allow for the simulation to start not at time 0 but also later. It gives flexibility. Okay, good. Now we can go with the simulation. And in the simulation, first of all, what we need to do is to set W1 equal to W2. At the beginning of the time step, we have to set WT equal to WT plus 1 at the previous time step. So this is the first thing that we have to do. And then we can compute, we are at the beginning of the time step now. So at the beginning of the time step, we first set W, which is the storage in the catchment, equal to the storage in the last time step. Okay, we are at the beginning. Now I compute the C1, which corresponds to W1. And how to compute it? This is the instruction. Let me go to the web page where iMod is described, because there I have the expression, the analytical expression for C1. So let me go back. Here we are, and let's compute C. Sorry, C is here. It's this one. Sorry, let's do that. This is the relationship that I need to translate into a line of code. Okay, so the translation of this image of this relationship is there. And given that I am using W1, this gives the value of C1, beginning of the time step. Look, when you have to interact with people, show your results, show to policymakers and the public what you did, a trivial suggestion that I give to you is never show a code. It's better to show the formula, or even better, a figure which explains what you are doing, because a line of code is not good for communication, and it's much better to never show the code. It's much better to show the analytical relationship, or even better, using an object-oriented way of communication, meaning that you show a picture and you explain what you are doing. Okay, now let me go back to the code, because we need to set up a code. At this stage, we can compute C2. C2, what I have to do is to get C1, add rainfall. But remember that I have to make sure that the value of C2 doesn't exceed Cmax. So this is why there is a min function which is used there. The min function means that if C1 plus P is lower than Cmax, then I get, as value of C2, I get precisely C1 plus P. If, on the other hand, C1 plus P is greater than Cmax, then I take as C2 value, I take Cmax. Okay, now we can compute at the stage year 1. Year 1 is the exceedance of Cmax. And what I need to do, let me go to the website to get back the expression for year 1. So I change the page. Year 1 is here. It's the max between CT plus PT minus Cmax and 0. And this is precisely what I find in the code. If you go to the code, is max P plus C minus Cmax and 0. Okay. Now I can compute W2, which is the storage after rainfall. Okay, so I update the storage into the catchment, and the relationship that I have to use, again, I jump to the website here. The relationship that I have to use is this one. Okay, where I use C2 as CT value. Okay, let me go back here, and you see here that I used C2. Just 1 second, it's a bit slow. Okay, perfect. At this stage I am ready with this line which I am isolating to compute here too. Very good. And here 2 is computed. Let me jump again on the website. 1 second. Okay, here we are. Here 2 is here. Okay. Now let me go back to the script. Now I can compute evapotranspiration, and there is the formula again on the website, so forgive me if I go back again, and the relationship is this one. Just 1 second, I am selecting it. It is this one. 1 second, it's a bit slow, the connection. I open it. Perfect. So this is precisely that computation. This is the translation. Good. And now I just need a couple of instructions before the break. The first one is the condition that W2 is not lower than 0. I think this condition should be better placed above when W2 is computed. The value of EP, it is taken here. Just 1 second. EPI, yes. I saw your question. The question is related to this relationship here. So let me go up in the file. I move upward now. I'm waiting for my connection to reply. And let me see, where is, I think EP was, okay, then I reply to the next question. EP was, let me go to the console. I think EP was defined here, but maybe that you are right. EP, you see, and look at the console, please, which is appeared in the right part. It's when we uploaded the data, when we uploaded the rainfall and evapotranspiration data, we defined the EP. So it is already into R. And if my reply is not clear to you, just let me know. And then there is a next question, which is why ER2 is computed with a max function. Okay, I tell you, just 1 second. I need to go here. Here we are. Because, you know, here too, just one second, because okay, here too shouldn't become lower than 0, and here too may become lower than 0 if W2 is lower than 0. And so we have to make sure that when we compute ER2, which is again, it's given by C2 minus C1 minus W2 plus, because it's minus minus, W1. Now, if W2 is lower than 0, it may happen that here 2 is lower than 0. We cannot admit that a river flow is lower than 0. And therefore, in any case, let's put here a condition that it's not lower than 0. Also, there is a condition here that W2 is not lower than 0. You can place it here, or you can move it up there. Let's see. You could move it here. In this case, if you put the condition up there, then probably you don't need to use the max function in the computation of ER2. But I suggest you to leave it there, the max function, because, you know, whatever it happens, let's make sure that ER2 is not negative. Also, look, yeah, no, I think, sorry, W2 0 should be placed here, where it was before, after the computation of EI, after the computation of this. This is why it was placed there. But then it is clear that you need a max for the computation of the ER2. Okay, I hope I answered your question. So there are a sequence of instructions to make sure that both ER2 and W2 do not get lower than 0. So here it's the condition on W2, and then here there is simply the sum, the computation of the total runoff as a sum of ER1 and ER2. That's it. Okay, I suggest that we make a break now, and then let's take 15 minutes and see you in 15 minutes from now. If you have any question, just take the next 30 seconds as an opportunity to ask on the chat. Okay, here I am. There is a micro open. Somebody, I could also make an attempt. I think, don't do anything. I think I have the opportunity to try an option to deactivate. Okay. I think I deactivated your audio, but it's not really what I wanted to do, because okay, let's see. I'm not sure whether you are still allowed to speak or not. If you're not allowed, write on the chat and tell me something. I think so, but I think what I did should have just turned off temporarily your microphone. Okay, now let's go and we got here. Now we have to subdivide the surface runoff in two components, you remember, through alpha, and then here it is. The two components are U quick and U slow. So sorry, I think, yeah, okay. and it is correct. I was just checking that everything was fine. And this is also what you should do. While we are discussing this code, check if everything is fine to you. And so uquick is given by the multiplication of alpha times ERI, and uSlow is 1 minus alpha ERI. So mass balance is, of course, is assured, given that we admit that alpha is a weight, so it's varying between 0 and 1. Okay, now there is the computation of the slow flow. This is just the application of the linear reservoir. It is written in a way that may look not really clear to you, unusual, let's say, and it's based, if you look at the second equation, first and second equation, it is based first on the computation of W slow, which is the water content of the reservoir, of the lower reservoir, and of course there is the computation of uSlow, and then there is then the computation of the outflow. Basically what you see here is a way of computing it that takes into account at the same time the fact that you have an entrance of flow given by uSlow, and at the same time you have outflow from the reservoir, which depends on kSlow. So this way, which I selected to compute the storage into the reservoir, it's a way that allows you to take into account at the same time inflow and outflow, which is in a way more precise, more correct with respect to the approximation that we used in the linear reservoir code. And I need to put a comment on this in the code on my website, because to highlight that this is more precise, put a comment in linear reservoir, I take a note. Okay. And then there is the computation of the outflow, which I am selecting here, depending on the storage of the reservoir. And this is simply done by these two lines because it's only one reservoir, the slow. Okay, now here I think that what we should do to be consistent with what we did before, it's put a 1 over k here and a 1 over k here. Because you remember that we decided in the code to change the kSlow with its inverse in order to be consistent with what we did in the linear reservoir. Okay, then we need to move to the computation of the quick flow. Here we have 3 reservoirs, and we have 3 reservoirs, 3 storages. In fact, you see there is, first of all, the definition of this, the initialization of this variable, qquick, which is the outflow from each reservoir. And then there is a repetition, a cycle, 3 times, because we have 3 reservoirs. If we want to change the number of the reservoirs, to add more or to decrease the number, we just have to change this 3 to the desired number of reservoirs. And then there is a computation which is similar to what we just discussed above for W slow. Now we are computing W quick. And again, here we have to put 1 over K and 1 over K. And then there is the computation of the outflow, Q quick, from each reservoir. Okay. And then here 1 over K, 1 over K. And then here, at the end of the story, we need to equate the outflow from the last reservoir. We equate it to U quick, which is our contribution to the quick flow at the closure of the catchment. Okay, this it's something that it is not strictly needed. It's just to be consistent. We call the U slow the slow contribution. We call now U quick the quick contribution. And then we have to sum the total flow. QT is equal to Q slow plus Q quick, and here there is the conversion factor. I decided to put the conversion factor here. We could have also put the conversion factor in the rainfall vector at the beginning. It's just a matter of personal choice. Okay, now here there is an option to draw a plot. If we want a plot to be drawn, then here is the plot. It's a usual plot function, and it's just put under an if, because it may happen sometimes that you get a value of the river flow that is too high, because if you put parameters values that are not appropriate, it may happen that the result gives you a meaningless computation. And therefore I put the if, the plot function under a if, because I just wanted to make sure that I don't draw a plot that is meaningless. This is something optional. You can also decide to drive the plot anyway. What may be suggested actually, and if the parameter vector is really very wrong, it may happen that you get infinity for some value of the river flow. And then if you get infinity, then the function may end up with an error. And especially if you draw up the plot. If you draw the plot and it may end up with an error. So it may be wise that at the end of the computation, one looks for the values of the vector qt to make sure that they are meaningful. I didn't put any general condition. I just put a condition on the plot. But also when we go to the next line, I explain to you what is this, but it's a computation on the river flow. And even here you may get an error if there are some infinite values in the vector qt. So I mean, it may be wise to put the condition of finite river flow, because what you see here, it's a condition of finite river flow. It may be wise to put a condition also before the computation of this function, because otherwise, as I said, you may get an error. But I don't think we strictly need it now, because we may say, okay, if I get an error, I change the parameter values. So it is something that is optional, let's say. And then what is this function here? It's a return, so it gives to you back a value. And the value that you see here, look at here, there is the difference, which is what I am selecting. It's the difference between the vector of the simulated river flow qt minus the vector of the observed river flows qos. This difference, ideally, if the model is perfect, should be 0. So this vector, which is which is a vector of differences, should be composed by a sequence of zeros. Actually, it never happens because the model is never perfect. And of course, this difference is an indicator of the reliability of your model. The larger the differences, the lower the reliability, and vice versa. So ideally, we want to get, as a result of this difference, a vector which has its values that are all close to zero. And these values in general are positive and negative. So we need to find a way, in this case, to quantify this difference. So how close are to zero the elements of this vector difference? How close are they to zero? If we just take their sum, if we take the summation of the elements of this vector, the summation may be something that is misleading because negative errors may compensate with positive errors. But if we square the differences, then we give a positive sign to all the elements of the vector difference, and then I can take the summation. This is precisely what is made here. What is made here is square before taking the sum. So I compute a vector of differences, I square it, and then I make a sum of the squares. Okay, very good. And I think what is the need to get this return function? The need is just to get a number which gives to me an idea of the model reliability. The plot gives to me a visual idea of the model reliability. Reliability because what I want to obtain is a simulation by the model which is as close as possible to the observed values. So if I draw a plot of observed values and simulated values, I get an idea, a graphical idea of the reliability. But it's also interesting to get a numerical quantification of the reliability. And the numerical quantification, one possibility is what you see here. This return instruction gives to me back this numerical quantification. The way it is computed, as I said, squared differences, sum of the squared differences between model and observation, we term it sum of squares. I'm sure that you already know this. The sum of squares is a numerical index of reliability of a simulation, reliability of a mathematical model. Sum of squares, and we will talk about it in more detail. Okay, I think we can stop here, and let me remove what you find down here. Okay, I remove it because I want to get in the script only the function. Okay, now let's save the script. And then I can source it. And let's see if I source it, what happens. If you have any questions, stop me. You see that automatically the console came up and it is fine. I didn't get any error. Let me source it again because I had a previous comment on the console. So you see there are no errors in the source. And now we are ready to run the model. What do we have to do to run the model? So first of all, let me take the console up here because now my attention should be on the console and the plot window, which will happen later. Let me clean the console. Are you ready to go with the simulation? Can I go? Write on the chat, please, yes, no, or questions. Okay, good. I just want to check if you are awake. You are. Okay, and and then oh, you know, there is no way. When I am in the classroom, sometimes it happens that students get sleepy, and also it happens to me when I attend conferences. Sometimes I fall asleep, but when you are in the classroom, I can check. Here it's more difficult, and I wanted to use this way of making pools, but still. Let me see. I don't think I can, and I don't understand why, because I am trying now to make a form again, because beforehand it was not possible. And let me see, question. I'm just making another attempt. I don't understand if it's a temporary problem or not. And let's see. No, still I don't have the possibility. I need to check. Okay, so let's go with the simulation then. My function is called imod. If you go to the console and you type just hy and then the tab, you see that indeed there is the function, and now you see the suggestion. The suggestion gives to you what are the arguments. This is great. Now I need to put parameters. So let's try in this way. The parameters as argument, I need to give a vector c. C is the instruction to give a vector. Let's try with the trial values 200, and then the second parameter, I think it is beta. Let's try with 0.5. The third is k, again 0.5. No, sorry, k alpha. And then we have the two k's. And the first is case low, I think. Case low, we can put something like, I don't know, let's try with 10,000. And the other one we can try with 2,000. No idea of what is coming out. I hope I didn't forget to make any substitution k 1 over k. Let's see. Let's try to just press return and see what happens. Figure margin too large, because I think the problem is that I need to open the plot window, and now I don't remember how to do this. Just 1 second. I think, okay. Let me try again to run it. I think it should work now. Okay, but there is something wrong. What we see is, first of all, let's forget about the fact that we don't have labels in the axis. So this is just a rough plot. And what we see is observed data, the black line. The simulated data is almost horizontal, which is something that it's not okay. So first of all, let me check if I didn't forget any substitution of k1 over k. Let me go here, and because I want to make sure, because, you know, let me see. Here is okay, 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 okay. And here, let me see. Seems everything okay. Yeah, okay. I think so. No, it should be okay. Okay, so let's go back to the console then. What I need then, if I think it is correct, I just need to change the parameters and see at the result here in terms of sum of squares. Just keep it in mind, okay? So let me change the parameters. I think the problem here is in the 2k values. They are probably too long. Let me try by removing 2 zeros, and let's see what happens. Okay, you see that there is a slight improvement, and still I think let's remove other 2 zeros. Okay, we are getting closer, and if you see the sum of squares, there is we are getting closer. It is now, let's try. If I remove again 2 zeros, I think it will be not good. Yeah, you see that now it's too peaky. It's too peaky. So I found a compromise. So let me try with something in between 50 and 10. You see that in terms of sum of squares, I think the other one was a little bit better. but still I prefer this one with respect to the other one. And there is one thing that I want to tell you, and I just said in terms of sum of squares, the past simulation was lower. I get back to you the past simulation, this one. You see that in terms of sum of squares, it's much better 172, that it's a little bit better 172 than 175. But if I look at the graph, look at the plot window, I prefer the other one. Let me get it back. I prefer this because I think it is overall it's a more reliable simulation. And then the consideration that I want to make is why I prefer this one, even if sum of squares it's a little bit worse. The reason is that I prefer this one because I am interested in the simulation of the low flow more than the high flows. And if I look just at the low flow, the simulation that I see here is much better than the previous one, which I am now redrawing. You see that for the low flows, there is a sizable underestimation in this case. Now, if I get to the other solution, underestimation of low flows is reduced. Yes, there is a way to make this procedure automatic, but let me make one step at a time, meaning that this is we are still considering a trial and error procedure. Why I'm doing this? Because if you make a trial and error, you understand much better what is behind what you are doing. If you run an automatic procedure, you don't understand the concept. The concept that I wanted you to understand by making this example is that if you lower the K values, you get a more peaky hydrograph, an overestimation of the high flows, because you see that now high flows are overestimated. But I just wanted that you have cleared this. If you get an hydrograph that is too flat, it means that the catchment has too much storage. This is the physical explanation. It means that in the model, you gave too much storage to your catchment. And how do we increase storage? If we increase the K values. So you have to keep this in mind because it helps you to find, to have always in your mind the connection between the math, the model, and the reality. Because your purpose is not to write a good model. Your purpose is to provide a good representation of the reality of the process. So it is very important that you use a mathematical model because we need it, but it's extremely important that you always have in mind the connection between your model and the reality. So I increase the K values, I see the hydrograph that goes up. Why is that? Because I increased the residence time of water in my catchment. K is the residence time of rainfall of water in your catchment. And if you increase the residence time of water in the catchment, you are increasing the storage of the catchment. And this is something that you have to get clear in mind, connection between model and reality. And if you run an automatic procedure, this connection is, it's more difficult to understand. So let's try to make one step at a time. At the same time, I want to tell you that I have always a doubt whether I am moving too fast or too slowly. So if you think that my level of teaching is too trivial, too slow, just let me know. This is not a problem. I can rush. So I could have skipped this step-by-step procedure, trial and error, and no problem. Just let me know your preferences. Maybe that because I am calibrated on the average preparation and background of students, but I see that this average background is increasing year by year, which is a very good thing. And also I am calibrated on classroom teaching, not remote teaching. I think that remote teaching gives the opportunity to go a bit faster. And but of course, let's I mean, what is important is your opinion. Just 1 second, I'm looking at the registration. Yes, it is moving forward. Yes, it is moving forward. So again, let's go back to our hydrograph. So sum of square is worse, but I prefer this solution. And the reason why sum of square is worse is that sum of squares, and this is another important consideration, keep it in mind, the sum of squares gives more weight to the larger errors. Of course, because you square them. So if you have an error of 1, you square it and it remains 1. You get an error of 10, you square it and it becomes 100. So you give more weight with this matrix to larger errors. And when do you make larger errors? When the river flow is higher. Because low flow is 2 orders of magnitude lower than high flow. It means that if you make an error in the low flows and you square it, it becomes negligible. Negligible in terms of the metric sum of squares that we are using. Okay, so it is understandable. If you are interested in the low flows, the sum of squares is not a good metric. And this is, as I said, another important consideration. But this is the last simulation that I did, but storage can be increased also by changing Cmax. So let's try to put Cmax at 400 and see what happens. And overall, I would say that this is not better, but on the other hand, maybe that this allows us to reduce again K. Let me do this trial. Okay, at this stage, you see that it becomes difficult to go by trial and error, because there is the combination of changing the Ks, changing Cmax, and then I can decide to change like beta or alpha. You see that with a different alpha you get, I didn't understand, yeah, you get a different simulation. This one is a little bit probably better for low flows, but it is really difficult to, we got the concept, but it is difficult to find the best combination. At this time we have to call into play an automatic optimization. This is precisely what Ludovic anticipated. Okay, now let's discuss about automatic optimization just a few minutes before I stop. And one more consideration before I move forward. What I did so far, namely to inspect the sensitivity of the simulation, sensitivity of the result, sensitivity of the model with respect to parameters, this is what I did. I inspected how much each parameter is influential on the final result. This is called sensitivity analysis. We are not discussing it because it's a bit too detailed, but it is a branch of science, a branch of the discipline of optimization. It is extremely important. You have to understand what parameters are more effective on your simulation. So we understood that the 2Ks are much effective. I understood that alpha is not very effective because you see that by changing alpha between 0.1 and 0.9 there is not a big difference. We can now check the sensitivity with respect to beta. Let's put beta 0.1 and you see that it's sensitive. Let's put beta 2. Again, this is sensitive. So beta is it's a very influential parameter. The model is much sensitive to beta. The model is not much sensitive to alpha. Okay, and now the automatic optimization. Let's go back to the script, because actually I removed from the script the instruction that I needed to perform automatic optimization. So let me recover them. and here it is. So there is an R function which is called optim, which we can use to make automatic optimization. There are several alternatives, several functions. Optim is okay. It's not the best one. And the other ones are functions that are not embedded by default in R. The alternatives are functions that I should upload. I think to start, Optim is okay. What do these functions, what do these optimization procedures do? Actually, they need to apply to a R function. So what is optimized? It's an R function. And here the R function is imod, the function that we just created. This function, to be optimized, needs to give back just one value, which is the value to be minimized. Okay, we want to minimize least squares. Fine, let's try to minimize it. And then they need other arguments. The function, and we will see what the arguments are. The function just looks for the combination of parameters that produces the best value for the least squares. And the way she looks for it is just making trial and errors attempt. They are guided, meaning that the function doesn't blindly look for the best combination. The function adopts a guided search algorithm, and different functions differ for the type of algorithm which is used. Okay, we don't go into details. We don't need to go into these details. We just need to get a result which is reliable, and this is something that we don't need to inspect. If we use a software to compute the river flow, then like imod, the imod function, we need to know how it works. If we use an optimization software, we don't need to know how it works because it's a mathematical detail. We just need to make sure that the final combination of parameters is what we are looking for. Okay, so now let me copy this function, this instruction, into the console. So I selected it, copy, and then let me go to the console. Here it is. Let me clear it, and let's paste it. And so let's see what's written here. So the function is called optim. It wants an initial parameter vector. She asks you to say what is the starting value of the search. Let's put here not 1/10, but 10 and 50, because we changed k to 1/k. Then it needs the name of the function, imod. The search method. Okay, let's take this. The lower value for the parameter vector and the upper value. It is extremely important to give these boundaries. And then there is a final instruction, which is given, a final argument given in the form of control. This is the tolerance to reach convergence. And it's basically a stop criteria. We can tell the optimization procedure to search until a very precise convergence is needed, but this can take a lot of time, or we can reduce the tolerance to be faster. I'm not sure what is specified here is a good tolerance. Let's see. Let's run it. One thing, we have the plot function at each time step. This is useful because at each iteration we can see the result, but it slows down the procedure a lot. So for educational purposes, it's nice to see the plot at each time step. For application, for professional purposes, it's better that you speed up the procedure. Now let's run it in this form. Let me see. I don't understand what happened because I'm not sure it got it in the right way. Let me see. Let me see if I can remove these spaces, because actually it didn't run. Okay, now let's try again. No, still there is something wrong. Okay, let me now one second. Let me try to remove these new lines, because I think probably it would be better if I, let me see. Okay, let me try to do this. Just one second. I'm copying it on a text editor because I want to remove. Yes, correct. This is correct what you say, but I don't think this is the problem. Let me try to. You're right. I don't think this is the problem. No, it's not the problem. First of all, let me see if Optim is here. Yeah, it's here. Sorry, I just wanted to. Want to see if yeah, Optim is there. Okay, and then let me see if there is an error message, no feasible solution. So I don't. There is something that I am missing. Something trivial that I am missing. Let me check. iMod, okay. Okay, sorry. Lower and upper, I need to change it. So this is 1000. As I said, there was something trivial missing, and this is 200. 200, and then lower is 22. Now it should work. Let's see. Okay. It is working, but still, let me see the plot. Okay, now now it is working, and on my screen probably is too slow for you to see, but I hope you got it in your PC. Now I think it's already converged, so let's see the result in console, and the result is here. These are the optimal parameter values. I think the value of the function is yeah, it's not bad, and probably the convergence, I think we could look for something better. Let me try by changing the tolerance. So 1e to the power 15. Let me try to put e to the power of 10. Let's see what happens. It's working. This is already quite good, actually. But you see that it's looking for more solution. It's trying to refine much more the solution, and this is because I changed the tolerance. And now it's close to convergence. You see that there is no much difference between one simulation and the next one. And I think we are close. It's still working. So I think this tolerance is too much. And because it may continue for a while I see that the graph doesn't change much. So let me stop it. And I think the solution is in between. Let me put 13 here, and then should be a good compromise. In any case, I think we got to target. This is what I wanted to show you in terms of automatic optimization. And this function is okay. I mean, it's by changing, finding the optimal tolerance, I think it gives a satisfactory output. And there are there are other functions which, in my opinion, are more effective. But I would say that even this result is not bad. Yeah, now we ended up with the routine, and if we look at the result, you see that the value of the least square function is quite good. I don't think we can get a much better representation. And here there is the combination, the optimal combination of parameters. So, and you may try, if you want to check whether the optimization was good, you may try to run iMode with this combination of parameters to see if everything is fine. This is a check that I recommend you to make. And so let's do like this. Let's clear the console. Oops, sorry. Let's clear the console, and I forgot to copy the combination of parameters. Let me get it. It's here. Okay, copy. Good. I clear the console. I want to get these here, and let me put them in a vector. Before I move forward, so this is a vector which I can call par1 equal c, sorry. Okay. Before I move forward, if you look at this parameter, which is alpha, I think it got the lower bound. When you, after an optimization, see that the routine collapsed against one of the bounds of the parameter values, this is not a good sign. It means that you have to change the boundaries, because it may happen that for a value of alpha lower than 0.1 you gain a better simulation. But for now, let me check if everything is fine in terms of trying to simulate with the given combination of parameters. Yes, you see that indeed we get the output that we were expecting. So that's it. Any question? Okay, I think I can also stop the recorder.